My name is Jaime Burbano. I'm an IoT solutions architect and a researcher at Fachhochschule Dortmund. And I'm here to present you our view on service quality management for edge critical applications. As we have here already the complete day, right? There are a lot of workloads now that demand not just high computing power, but they also demand low latency and also stable latency. So we will say, wow, the edge is already fulfilling those requirements. It sounds quite obvious, quite simple. However, if we really think about it, the edge is not that reliable. There are a lot of sources where we can get fluctuating service quality. I'm pretty sure you have seen these latency spikes. All of a sudden, we have worked with some companies, they say, I don't know from where they come. Just try to figure out. My customer is not happy. I don't know what to reply to them because I don't know what is the source. And what is the main problem is we do have a critical lack of visibility. There are several tools that we have developed also in the CNCF community, such as OpenTelemetry, Prometheus, so many more. However, there is still a lack of visibility in the sense of me being able to understand from the bottom to the top. By bottom, I understand the user-equipped device, then we have the network, and then we have the edge infrastructure itself. There is a lack of an end-to-end view. So if you just see here this typical edge infrastructure, I'm pretty sure you already identified several places where we can have several service fluctuation problems. In the devices, in the network, it is too congested, the traffic is not good, the network path I'm taking is not proper. And when I go to the edge, I can have a lot of workload there. Therefore, let's say I have an inference of pedestrian detection. It takes too long. Just imagine the automotive taking more than 200 milliseconds just to detect if a pedestrian is nearby or not. This is obviously not possible in edge computing. So what we say is, in edge, fluctuations do make a big difference, and we need to do something about it. It's not that easy, but we have been working in an end-to-end scheme that assures you to have edge service quality in edge computing scenarios. So to keep it simple, we basically monitor the complete edge chain, that is to say, devices, network, clusters, edge servers, and applications, collect all this data, analyze it, perform some correlations, understand what is the source cause or the root cause of this service quality degradation, plan a mitigation action, and obviously execute it. So if we see it a little bit more in detail, still high level, what we do is we deploy distributed collectors in the client. We also collect information from the network, and then we deploy these collectors at cluster level and worker node level to collect all this data using different technologies, as you can see here in the slides. And then we put everything in a single place. We run ML models to identify what is the run or the source cause of this problem, such as you can see here, right, the risk. We determine it, and then we execute or plan different actions. So now you will be wondering, okay, cool, these guys are monitoring what they can do, right? Some of the examples that we can create is these service planners that we call them, and you can do this type of applications. These are just examples, but you can think in many more. First of all, if you're able to understand how the network is behaving, you understand also how your servers are performing, you might tell this vehicle, if you go to that edge, it is not the best because the network path is very slow. Why don't you pick this edge server? Because network path is better, but also it has a better GPU, right? It can perform better. It can give you a lower latency. So we can even achieve granularity of as per request in these edge critical applications. Other situation could be when we scale up or scale down the resources in the edge cluster, for example, to have less latency or to save energy. Now imagine, okay, you have a 5G network, pretty cool. You're assuming it's very fast. You run your application, but you realize that the network is not good. Your infrastructure at the edge is very good. You have put enough resources, but the network is not working properly. So with this feedback loop, we can simply monitor and say, the quality issue comes from the network. Let's scale up the resources on the edge server to compensate for this performance degradation. And if you think about it, we are closing this loop, right? We monitor, we act, and then we simply give a feedback. And last but not least, another very cool use case that we have is that we can dynamically partition the workload. That means that we can say, given these conditions, why don't you run certain portion of the application in the client and let the rest run at the edge? if the edge is not working so good, you may run more in the client, right? Then you are saving latency or saving energy based on what is your service level objective. Well, this is a very simple view. What you are seeing here is the edge latency and jitter profile of an edge application. In concrete, this application is a traffic detect sign, more or less AI-based, right? So you see here is the end-to-end latency of this application, right? With our solution, we are able to not just monitor, but we can also generate control events, such as network load or CPU load in the server that is running the application itself. So you see here we have the spans. Basically, each one of the spans represents a segment of this application, rather the client pre-processing, which is, of course, grabbing the image from the camera. Then you have the data transmission, sending it to the server. Server processing means analyze the image and get the prediction. In this case, as I said, traffic sign detection. And client post-processing is the analysis that I need to do once the response from the server comes back. So with our tool, we are able to trigger network load and CPU load. As you can see here, when we trigger network load, the span that represents to data transmission obviously get high. And therefore, end-to-end latency, or the increasement in end-to-end latency is due to this network failing. Something similar happens in CPU load. When we trigger CPU load, you can see that the jitter of our application simply gets crazy. So now I could say, okay, this seems to be pretty simple. Okay, yes, but the input that you get here then gives you actions that you can take. And let's remember that this is not the only thing we collect, right? We also collect information from the rest of the infrastructure itself. So when we start correlating all this data, you can really get very good insights into what is the root cause of your problem. This is a little bit of an example. Due to the time, obviously I cannot guide you through it, but there's a small or huge QR code, right, that you can just scan it to look the full demo. But basically what we do here is we have a small vehicle which is running a DNN model for inference of a track detection. It is just getting the images, it processes the image, detects the tracks, and then it tries to follow. It tries to go into a circular track. When the model is running at the edge, right, nothing is wrong, everything works fine, the vehicle remains into the track. But when we start triggering this load, rather in the network or in the edge server, obviously the time it takes to get the inference back and get the steering commands will get longer. And that means that the vehicle starts to deviate from the track it should follow, which of course reflects a huge problem when we talk about edge critical applications. So what we do is we install and we run our service quality manager, SECAM, which is able to understand all this data, collect it, right, analyze it, and then as we have also insights about the application, we can select the proper partition strategy. This may sound a little bit weird, but if you remember, we had this dynamic workload partitioning. So what we do is we say, okay, this DNN model behaves in this way. I understand the amount of computing that each layer requires. I understand the amount of data that each layer sends to the next one. I do know how the network is behaving. I know if it is good or bad. I know how much my edge can process. And then we say, given all these conditions, what is the best partitioning layer that I can take to make sure that I complete or I fulfill my service level objectives? Let's say I always want this thing to run below 100 milliseconds. Then our algorithm will say, yeah, if you partition in layer 2, you will get the best latency, which fulfills your objectives, and also you could save energy on the device. So this is more or less what we have given to you today. We are really happy to get any feedback, and also if you are eager to collaborate with us in the field of service quality for edge computing, we will be more than happy to get in touch with you and get to know you a little bit better. Many thanks.